So far we have discussed about the optical system and sample handling. Okay. Now, we will continue our discussion about the radiation sources in infrared. Now, most of the commercial instruments use an extended source close to that of a black body radiation, similar, close to means similar to black body radiation around 1000 to 1500 Kelvin. That means, you take any substance, black substance, metal, heat it to 1500 to 1000 to 1500 degree Kelvin. So, that is about 1300 to minus, make it minus 273, that makes it around 800 to 1200 degree centigrade. That will make this material glow red, and any material that is glowing red because of the heat, it throws out infrared radiation, that is the assumption. So, most of the black body radiation materials around 1000 to 1500 give out infrared radiation. I can use any of them. So, what are such materials? Such materials are nichrome wire, that is nickel chromium alloy, nichrome wire. I can use a Nernst glare, I can use an Oppermann and a Glober source. These are all technical names, Nernst glare, Oppermann and Glober sources, but nichrome wire everybody knows that it is nickel chromium alloy wire. They are commonly employed as sources of infrared radiation. So, how many of you have seen a nichrome wire? If I ask you the question just like that, many of you would say no. But if I ask you, how many of you use a heater in a coil at a, when it is very cold, heater in a room, and how many of you use electric heaters for in the kitchen? You know, earlier there used to be in the kitchen electric heaters with wire wound round and round in a ceramic base plate. Even now they are available in the market, and you just have to switch it and connect it to a plug. The wire will glow red, and that is nichrome wire. Okay. So, the nichrome wire, I think many of you must have seen it, and these nichrome wire is a very simple, is used either as a simple coil just like what you see in electric heaters, or it can be supported on a ceramic rod. I can take a ceramic rod like this, a pen, and I can wind the nichrome wire around it, and then connect the two ends and then heat it. So, the wire will get heated and start giving out infrared radiation on all sides. So, put a mirror behind it and everything will be reflected to get a parallel beam. Okay. So, the nichrome wire, I am sure most of you must be aware that it is a very simple system and it must be very cheap also. It is not very costly. So, most of the low and mid price instruments use nichrome wire. Why not? And it can be replaced. You know, quite often the nichrome wire gets cut and the IR radiation will not come because of the short circuiting or breaking of the wire. So, it is easy to maintain, and so long as it works, it is good enough. So, prolonged use can lead to oxidation. Sometimes wire gets oxidized to oxide, and oxides are not good conductors of heat and electricity. So, you have to heat it more and more to make it look red, and the more you heat it, the more oxide will form, the less heated it will be. At some point a breaking point will be reached, and then thermal stress deforms the coil shape, and quite often it breaks into two. The connection is gone. So, the long term stability and output are affected over prolonged use, but quite often these are all very simple. You can buy a huge coil of about 1 foot or 10 foot coil, and whenever it gets cut, you just go there, replace the wire, refix it and then start reusing. That is the nichrome wire for you as an IR radiation source. Okay. See, what I am trying to tell you in most of these instrumentation is none of them are really high tech equipments, but they are made to look high tech whenever an instrument manufacturer comes to sell you an instrument. He says, sir, we got only nichrome wire, this thing we will give you spare wires, so that you can use them like that. But in actual fact is you can go to market and buy nichrome wire and use it yourself. So, the instrument manufacturers make use of your ignorance whenever they are trying to market their equipment. So, there they make their money. Okay. That apart, the nichrome wire is available everywhere. Okay. Second one is Nernst Glower. So, Nernst Glower is a mixture of rare earth oxides. Just now I was telling you that if the metal forms oxide, it will not glow red, it will take more heat and it may break the conductivity. Now, the rare earth oxides, they are oxides only, and then made it into some sort of a small pen top, molded into a piece like this. Okay. Oh, it is not visible here. Okay, does not matter. It can be molded into a piece like this, about 2 centimeter pen portion what I am showing you, and it can be pressed, hard pressed into a small cylinder which can be connected at both ends. So, this rare earth oxides, these rare earth oxides are heated by electric current. You have to supply electricity to make them glow red hot. Okay. So, this has got, that means you have to heat them at very high temperature. So, it has got negative coefficient of electrical resistance. You should remember this, because anything that has got a negative coefficient of electric resistance means its electrical conductivity increases with increasing temperature. Most of the metals have the property other way around. You take the metal, you start heating it, its electrical conductivity comes down. Okay. But oxides, rare earth oxides behave the other way around. You take the rare earth oxides, make it into a small pellet, connect the electrical wire, start heating it. As you heat more and more, the more conductivity becomes better and better, unlike metal. So, the external heating is required initially. Okay. So, you cannot heat the electric that rare earth oxide wire directly by electric current. First you have to connect it to an external heater, supply that heat to the Nernst glower, and slowly as the temperature increases it will start glowing. So, at that point you can cut off the primary heater, and then after some time this itself will take over as the IR radiation source. So, its electrical conductivity increases with increasing temperature. So, external heating is required. This adds to the cost, because I have to provide extra additional heat to the in the instrument, another circuit to be added. So, it must be carefully regulated to control a runaway situation. For example, if you uncontrollably heat, then the rare earth oxide will also get heated to very high temperature, and we do not need that, because its life also will go down. So, it may start heating it unnecessarily to very high temperatures, which is not ideal. The Nernst glower has got this property, that is rare earth oxides. Now, the Opperman is another type of IR source that consists of a ceramic rod filled with again rare earth oxides, but with a coaxial metal wire located inside the center. Now, you can understand it will be something like this. I have a rare earth oxide here and I made a small piece, a cylindrical piece, but I do have a small metal wire here inside. This is metal wire. This is rare earth oxide cylinder. This whole thing is about 3 mm. This will be about 5 centimeter, maybe sometimes 2 centimeters also. Okay. So, this is here I have a metal piece to aid the heating. That means one single instrument will take care of the total arrangement. So, you do not need a second circuit, unlike Nernst Glöer. So, with a coaxial metal wire located inside the center, Oppermann is designed. So, the wire is heated first, which in turn heats the oxide mixture. This is self regulating and does not require any additional external heating. So, whenever you buy an instrument, you have to really think what instruments you want to, what source you would like to have. Usually you ask the manufacturer what source you are giving for us in the IR, so that if the IR radiation stops coming out, I need to replace the source. So, the source, is it nichrome wire, Nernst Glöer or Oppermann or the Glober. So, I have not taught you about the Glober yet. So, what is a Glober? The Glober is essentially an electrically heated silicon carbide rod. It is basically a silicon carbide rod, just like this pen. Okay, a small piece of pen about 2 mm thickness and 3 centimeter or 5 centimeter rod, which can be connected at both ends to the electrical wires for heating. So, that is silicon carbide wire. It is essential to help stabilize the source and reduce the heat dissipation to other components in the instrument, because silicon carbide can be heated to very high temperature. So, the heat should not be passed on to other components of the instrument, which may melt, which may deform, and it may lead to shock, etc. So, heat dissipation has to be taken care of. So, the typical lifespan of silicon carbide source is about 2 to 5 years. So, most common failures, how do they occur in silicon carbide? They break. They, as usual, they develop hot spots or loss of power by oxidation of the electrical connections. It is not the electrical wires, but it is the connector that is happening. So, that is about the detectors. Okay. Now, I want to talk to you about the detectors. The most common detector in infrared radiation is thermal detector or photosensitive quantum detectors. They are useful in infrared spectroscopy. Thermal detectors normally sense temperature changes by a change in the physical property, such as generation of voltage, or they can change the resistance also. So, the speed of we monitor the resistance with the radiation once and without the radiation other way another time. That is, whenever I want to take the blank 100% transmittance, just like in laser IR, I just use the laser without the sample, that is 100% this thing. I just monitor the resistance and then put the sample, monitor the resistance. So, the speed of the thermal detectors basically are influenced by the thermal capacity or the heat capacity of the detector element, which is somewhat lower than photon counting detectors, the efficiency. So, the response of the thermal detector is actually independent of the wavelength of the incident radiation. It has to be, no. So, the incident radiation whatever it is, but the response of thermal detector is depends upon how much photons are coming out of the detector. So, I can use a thermocouple. You know what is a thermocouple, isn't it? Many of you must be knowing. Thermocouple is a two metal strips fused together to give you one single connector, and at the juncture it gives you the different current. So, the thermocouple is another way of measuring the heat changes that occur in the infrared spectrum of the incident radiation as well as absorbed radiation. So, absorbed radiation will have less heat output compared to the unabsorbed 100% transmittance. So, the pneumatic detector and another way of detecting infrared spectrometer spectrum is by pneumatic detector or a Gole detector, that is a name detector, and we also use what is known as bolometer. Different kinds of detectors are used, and thermocouple, pneumatic, Gole detector, bolometer, these are all different kinds of detectors developed over a period of time, and most of them are into regular use. Not that they are in any way better than the existing ones or better than, they do have certain advantages over others. I am not going into the details, but I am just going to explain to you the the principle in general. So, the response of the IR response of the temperature changes are of the order of about 10 raised to minus 1 to 10 raised to minus 2 Kelvin. That means, the sample difference between the reference sample and the actual sample, the temperature of the incoming radiation, generated radiation is actual sample, is the generated radiation is actually the unabsorbed, and once the sample is put, I have the lower temperature because part of it is absorbed. So, the temperature, the radiation coming out of the sample is much less when part of it is absorbed. So, what is the difference between the absorbed and unabsorbed radiation? Delta T we are looking for. The typical delta T for optimum detection is 10 raised to minus 1, that is 0.1 degree Kelvin, or 10 raised to minus 2 degree Kelvin. Okay. Now, we do not say degree Kelvin, we just say 10 raised to minus 2 Kelvin, but 1 Kelvin and 1 degree centigrade both are same. I think many of you must be aware that what I am saying is the scale is different, but the magnitude of the heat is essentially same. So, 1 degree Kelvin, 1 degree centigrade both are same. So, but only because of highest international standards we use degree Kelvin in such expressions. So, these are used extensively in dispersive type instruments, and sometimes we do use bolometers. Bolometers are used more in infrared instruments, IR. So, essentially what we are talking about, the Gole detector and thermal detector, Gole detector as well as bolometers, they are all thermal, and the temperature difference is about 0.01 to 0.02 degree centigrade or Kelvin, and these are used extensively in dispersive instruments, that is prism, grating, prism grating or grating instruments, not in FTIR. In bolometers are used in FTIR. Why? I will just give you a couple of seconds to think why we use bolometers. Many of you may not even be knowing what is a bolometer, isn't it? Just go home and check. I will give you this as an example in the instrumentation course. You can try to find out what is the answer to this. So, what is a bolometer? Okay. So, the bolometers are used in infrared FTIR instruments. Okay. Now, the thermocouple, we go one by one again, some good and bad advantages, good and bad factors. As far as thermocouple is concerned, it is fabricated with two dissimilar metals such as bismuth and antimony. You can produce many thermocouples with different chromium, nickel, some I had already told you, platinum, rhodium, several kinds of thermocouples are there which can be used for temperature monitoring in infrared. Temperature monitoring of what? The transmitted light with the sample once and without the sample another way. So, the ratio provides the infrared spectrum with this ratio with the sample and without the sample. Okay. So, a small voltage is produced when the dissimilar metals are used. The dissimilar metal piece fused together is used for making the IR radiation fall onto that joint where they are fused together. So, the junction, it is called a junction. So, the junction temperature should be monitored whenever we use infrared spectrometry. So, sometimes we need several connectors in series for additional output. Half of these junctions are hot and containing the active element, and alternative junctions are cold. Okay. So, these hot and cold junctions are thermally bonded to the substrate. Now, what is the substrate? It is the detector body. Okay. So, it may be fixed on the instrument itself. So, these substrates retain the temperature at a slightly lower rate than the only outside the instrument. Okay. So, thin film techniques have miniaturized the thermocouples. The entire assembly is mounted on an electric evaluated enclosure with IR transmitting window infrared, so that the conductive heat losses are minimized. The response time is approximately about 2 hours, not more than that. Okay. And it is not response time is not 2 hours, but it is 80 microseconds, not 2 hours. It is 80 microseconds. So, if the IR radiation changes the signal within 80 microseconds, it must show on the recorder, then only such detectors are used. Okay. Now, here I am showing you the cross section of a thermocouple detector. So, you can see I have here the whole size of this detector is about 5 centimeter. Okay. Such two detectors are used, and it uses a P type film and N type film, NP type film, and here the film is exposed in this area. Okay, I will show you here. So, the film is exposed over a very small portion here and another small portion is here, remaining is black painted. Okay. Now, there is an oxide film here at the bottom of that plating, and this is these are the two metals. Okay, you can see the two white lined areas below this black paint. Okay. And there are two different metals, one is the sensing junction, that is hot, another is the oxide film, that is cold. So, the oxide film is at the bottom and sensing junction is at the top. Okay. Now, the other parts, this is a output pin. Okay. So, this is how the whole thing is mounted. This whole thing is mounted on this box. Okay. And then there is a header to fix the detector, and they are welded, and one more support you need, and this support is it gives a small gap here in between, and I put a small window here. This window, if it has to allow IR, it has to be made from polythene film or sodium chloride or whatever is the optical quality that is required for our infrared. Okay. So, the aperture is IR transmittive and window is IR transmittive. All the radiation will fall, this black radiation will absorb the radiation, but it is of no use, but I have a small transparent piece here where the radiation will cause generation of the current. One is cold, another one is hot. So, this is reference, cold is reference junction, the other one is aluminum, another is hot junction, and this whole thing is mounted on an aluminum, this one, this portion. Okay. This red portion is aluminum piece supported required to take out the heat generated by the IR. So, as the infrared radiation moves from one frequency to another, there will be a peak generated based on the temperature difference. The moment the infrared radiation moves to another region where there is no infrared radiation or infrared peak, the heat generated must be dissipated. So, that heat generated is dissipated using this aluminum heat sink, that is known as aluminum heat sink. So, this is how a thermocouple detector is designed in infrared spectrometers. It is a fairly decent engineering item, but we should understand how a detector works. So, here is the wavelength response of some IR detectors. For example, I have plotted here the detectivity, that is detection at lambda around 900.1 centimeter hertz. Okay. This is 10 raised to 9, 10 raised to 10, 10 raised to 11 hertz raised to half and wattage raised to -1, and here it is wavelength. Okay. Now, I have different curves here 1, 2, 3, 4, 5, 6. First one is indium antimony detector, that is the bimetal, the thermocouple made of indium and antimony. It keeps on increasing from 1 to 5 micrometers, okay, and then it falls off. What is the wavelength required for us in the IR? It is 4000 centimeters inverse. No. So, this 1 to 5 centimeters, 1 to 5 micrometer nanometers basically is quite good, but not that good. Look at number 2, it starts from about 3 micrometers up to 10 micrometers, that is good. And then number 3 is it keeps on increasing from 1 up to almost 11, okay, green one, and then it falls off at higher wavelengths. So, that is lead, antimony and tellurium. This both are same 2 and 3, but a little temperature difference makes them work much better over the entire range. So, the whole thing is the research in these bimetal detectors is basically concentrated on how far we can take the detector, make a response up to 10, 11, 12, 13, 14 micrometers, and then how long it will survive and how many cycles it will survive, like that. Different what suppose pre-treatment temperature is 42 degrees or 77 degrees, how is the response? Lot of research goes on in IR detectors. So, look at number 4, it is just a pyroelectric wire at 300 degrees. Number 5 is a thermistor at 300 degrees. Number 6 is a thermopile at 300 degrees centigrade Kelvin. All of them are at Kelvin only. I should not say degree centigrade. Okay. So, a thermistor functions by changing the resistance when illuminated with infrared. These are made of sintered oxides of manganese, cobalt, nickel, etc. They have a high coefficient of resistance. One of these is active, which is coated black, and another is mounted to increase its IR absorption, whereas reference is optically shielded to prevent the IR exposure. Both are mounted on an insulating substrate placed on a heat sink. So, when connected with a bridge circuit, it compensates the ambient temperature drift also. So, the response time here is about a few milliseconds. What was the response time earlier with thermocouples? It was 80 microseconds here, but now look at it. These thermistors have few milliseconds. So, response of the thermistors are slightly lower than the thermocouples. They change faster, immediate response. So, we will take up the Gole detector and other instrumentation in our next class. Thank you very much.